This video is the review for the final exam. And so for the first series of questions, we're supposed to use the data in Table 1. And Table 1 gives us the mean and standard deviation for levels of education by social class. And we're told to assume that years of education are normally distributed. So the first question basically says, what's the proportion of working class respondents that have between 12 and 16 years of education? Well, from the table, we can see that the working class people have, on average, 12.64 years of education with a standard deviation of 2.5 years. And so we're looking for some area below the mean and some area above the mean. And we want basically the interior area. So in each case, we want the area between the mean and the z-score. So let's start by creating a diagram. Our diagram is going to look something like this. So this shows the normally distributed variable education. For the working class, we have 12.64 years in the middle, and we're looking for the area between 12 and 16. And so to answer this question, we basically have to take our z-score formula and find the z-scores corresponding to 12 and 16 and the corresponding areas for both. And then we're going to add together those areas, and that will give us the answer to our question. And so for the first part of our question, we're going to take 12 and we're going to subtract the sample mean, 12.64, and divide it by the sample standard deviation, 2.50. When we do the arithmetic, we get a value of negative 0.26, which tells us the 12 is a little over a quarter standard deviation below the mean. And we can do the same thing for 16. We take 16 and we subtract the mean, 12.64, and we divide it by the sample standard deviation, 2.5. We get a z-score of 1.34. Now we have to take these values, negative 0.26 and 1.34 respectively, and we have to locate them on the standard normal distribution and figure out what area corresponds to the area between the mean and the z-score for both. So let's start with negative 0.26. Now unfortunately that value isn't going to be listed because the standard normal table only shows positive z-scores. So fortunately, because it's a symmetrical distribution, the value corresponding to a value of negative 0.26 is the same as the one corresponding to a value of positive 0.26. So we're going to look at the column A in the table and find positive 0.26, and then figure out what area between the mean and the z-score corresponds to that z-score. So going to my table, I look at column A, I find positive 0.26, and now I'm looking at column B to figure out what's the area between the mean and the z-score. And in this case, it's 0.1026. I have to do the same thing for 1.34. So I'm going to look that value up in my standard normal table. It's here in column A. And then I'm going to look at the value in column B, which is the area between the mean and the z-score. And that's a value of 0.4099. So if I just take those two areas and I add them together, that'll give me the area that I'm looking for. And their sum is about 0.5127. And so we can say, in answering the question, that the proportion of working class respondents that have between 12 and 16 years of education is about 0.51, or about 51.25% have between 12 and 16 years of education. For the second question, we want the proportion of the upper class respondents who have between 12 and 16 years of education. And so we see from our table 1 that upper class respondents have 15 years of education on average, with a standard deviation of 3.27 years. So 15 is our average. That means we're looking for an area below the mean, because 12 is below the mean, and an area above the mean, because 16 is above the mean. So this diagram basically shows the distribution of education for the upper class respondents. 15 is going to be in the middle. 12 is going to be below 15, 16 is going to be above 15. And so just like for the last question, we need to turn the 16 and 12 into z-scores, find the area in column B, that is the area between the mean and the z-score, corresponding to each of these z-scores, and we're going to have to add those together to answer the question. So we can start by using our formula. The z-score is equal to the raw score minus the sample mean divided by the sample standard deviation. And we'll start with the value for 12. So 12 minus the mean, 15, divided by the standard deviation, 3.27, gives us a z-score of negative 0.92. And so that tells us that 12 is just about one standard deviation below the mean. Not quite there. 0.92 standard deviations to be specific. And then for 16, we'll take 16, subtract the sample mean, divide it by the sample standard deviation, and we'll find that the z-score there is going to be 0.31. And so that tells us that 16 is about 0.31 standard deviations above the mean. And so we have to look up both of these values. Remember, using the positive value because the normal curve only shows positive z-scores in the standard normal table, and the positive value here as well. And we have to figure out the area between the mean and the z-score in column B. So I'm going to start with this one. I'm going to look up 0.92 in my standard normal table. So that's here in column A. And I'm going to look at the value in column B, which is 0.3212. Next, I'm going to look up 0.31 to find its area. And so 0.31 corresponds to an area between the mean and the z-score of 0.1217. And so if I just add those two areas together, I get the answer to my question. And the answer turns out to be 0.4229. And so I can say that about 44.29% of upper class respondents have between 12 and 16 years of education. For question 3, we're looking for the probability that a working class respondent, drawn at random from the population, would have more than 16 years of education. And so to answer this question, you'll recall that the working class people have on average 12.64 years of education with a standard deviation of 2.5. And so we can start with the diagram. If our mean is 12.64 and we're looking for the area beyond 16, we're basically looking for an exterior area beyond the z-score. And so we're going to be looking at column C in the table. And so to answer this question, we'll take 16 and turn it into a z-score using this formula, which tells us to take the raw score, subtract the sample mean, divide by the sample standard deviation. And so that tells us to take 16 minus 12.64 divided by 2.5, and that gives us a z-score of 1.34. And so we're going to have to look up 1.34 in the standard normal table and look for column C. It's going to be the area beyond the z-score. So here's 1.34. Here's the column C value. It turns out to be 0.0901. And so that tells us that about a little over 9% of working class respondents have 16 or more years of education, and that's the answer to the question. For question 4, we're looking for the probability that a middle class respondent, drawn at random from the population, will have less than 12 years of education. And so recall that the middle class respondents have 14.19 years of education with a standard deviation of 2.39 years. And so if we draw a diagram, we're basically looking for some area that's below the mean, and we're looking for an exterior area, or an area in column C. And so what we have to do is you have to take 12, turn it into a z-score, and find the corresponding area in column C of the table. So again, we're going to use this formula. It tells us to take the raw score, 12, subtract the sample mean, and divide it by the sample standard deviation. So 12 minus the sample mean, 14.19, divided by 2.39. That gives us a negative z-score, negative 0.91. And so that tells us that 12 is 0.91 standard deviations below the mean. So a little less than 1 standard deviation below the mean. So again, there's no negative z-scores listed in the standard normal table. We'll look up the positive z-score because it's symmetrical. And we're going to look at column C. So we're going to find 0.91, and that's here. The column C value there is 0.1814. And so the answer to our question basically is 0.1814. Or we can say that there's the probability is about 18.41%, or 18.14%. And for the next two questions, we're given the following scenario. We're told that we have the mean family income for a large southern city, and the value for that mean income is $34,000 with a standard deviation, in this case for the population, of 5,000. And so this is going to represent our population data. The population mean is 34,000, standard deviation of the population is 5,000. Now we're told that we take a sample of 200 city residents, and we calculate the mean based on that sample. So the first question is, what's the probability that the sample mean is between 33,000 and 34,000? So we can start with the diagram, and in this case, what's being illustrated in this diagram is the distribution of sample statistics. In other words, this is a sampling distribution. And we know something about the sampling distribution. We know that the sampling distribution is normally distributed by the central limit theorem, as long as you have a large enough sample size. And we know that it's centered around the value of the true population mean. And so in this case, 34,000 is our population mean. That's also the middle of our sampling distribution. And so if we're trying to figure out the probability that the sample mean is between 33 and 34,000, as our question indicates, we're basically looking for the area from the mean to 33. And 33 is, of course, below 34, so we're looking for some area below the mean. And again, we're looking for an interior area. That is an area between the mean and the z-score. And so we're going to change 33 into a z-score using the formula for a z-score transformation. And now this time, because we're dealing with the sampling distribution, we have to use this formula. And this formula tells us to take the sample mean, subtract the true population mean, mu sub y, which is equal to the mean of the sampling distribution, and divide it by the standard error of the mean, which is equal to the true population standard deviation divided by the square root of the sample size. And remember, we do this because as we increase the sample size, the amount of variation in the sampling distribution goes down. And so first, we can basically just calculate our standard error. And so our standard error in this case is equal to our true population standard deviation, 5,000, divided by the square root of our sample size. And our sample size is 200. And so we get a value of 353.55. And now using that value, along with the other values, we can calculate the z-score for 33,000. And so our raw score in this case is 33,000. That's our sample mean. We subtract the true population mean, 34,000, and we divide it by our standard error of the mean, 353.55. We get a z-score of negative 2.83. And of course, that's not listed, and so we're going to have to look up the positive 2.83 z-score. And we can do that because we have a symmetrical distribution, so the same area for negative z-scores is the one for the positive z-scores. So 2.83 is what we're looking up. So we find that right here, and we're looking for the area between the mean and the z-score. And so that's this value, column B. And so that's a value of 0.4977. And so that's going to be the answer to our question. We're basically finding that there's about a 49.77% chance that the sample mean is between 33,000 and 34,000. Our next question is, what's the probability that the sample mean exceeds 37,000? And of course, if 34,000 is our population mean, then 37,000 is going to be larger than our mean. If we're looking for the area that exceeds 37,000, that means we want some area beyond the z-score, or an exterior area, basically the area in column C. And so we would go about this question by taking 37,000 and turning it into a z-score, and then finding the corresponding area beyond the z-score. And so we use this formula. Again, it tells us to take the sample mean, 37,000 in this case, subtract the population mean, which we know is 34,000, and divide it by the standard error of the mean, which we calculated earlier to be 353.55. And so if we do the arithmetic here, we get a value of 8.48. That tells us that 37 is almost 8.5 standard deviations above the mean. So that's a huge distance away from the mean. In fact, it's so large it won't be listed on the table. So if we go to our table, we can see that the highest value listed is 4, meaning that if anything is above 4 standard deviations, it's so large it's not even listed on the table. So we can't get the exact value beyond the z-score for this particular value, but we know that it's going to be smaller than this value. And so this value is already smaller than 0.0001. We can use that as a pretty good approximation. And so the answer to this question basically is that the probability is less than 0.0001, or less than 1 in 10,000 samples gives us a result like this one. For question 7, we're told to go back to table 1 to use the data on education across the social classes to answer the following questions, 7 through 9. And so question 7 says, construct the 95% confidence interval for the mean number of years of education for the lower class and the middle class respondents. And so when we're making a confidence interval, we're going to use this general formula. It tells us that the confidence interval for some level of confidence is equal to the sample mean plus or minus the value of a z-score times the standard error of the mean. So now let's start with the lower class respondents. So if we go back up to our table 1, we can see the lower class respondents have 10.34 years of education with a standard deviation of 3.18 years. And there's only 89 cases of people in the lower class. So there's a few considerations that we have to take into account. First, we don't have the true population standard deviation, so we can't get the value of the standard error. We have to estimate the standard error by using the sample standard deviation in the formula. And so we can't use a z-value, we have to use a t-value, because we're introducing additional sampling error that the t-value correctly takes into account. And so we have to find the t-value corresponding to our degrees of freedom, our alpha level, and the fact that we're using a two-sided confidence interval. And so we'll look at a portion of the t-table here. First of all, degrees of freedom are calculated by taking the number of cases, in our case 89, and subtracting 1, because we lose 1 degree of freedom by estimating the true population standard deviation with the sample standard deviation. And so we're left with 88 degrees of freedom. If we're using a 95% confidence interval, we're going to have an alpha value of 0.05. And we always have a two-sided confidence interval, so we're going to use the two-tailed version. So two-tailed, 0.05, and we have to find 88 degrees of freedom. Now in this table, 88 isn't listed, but we know it's between 60 and 120. And so the correct value for a two-tailed 0.05 level is going to be between 2 and 1.98. And so I'm just going to use the closest one. Let's pick the one for 60 degrees of freedom, 2, and we'll use that as our t-value in our calculation. And then for the middle class respondents, let's take a look at the middle class statistics from table 1. We see that the middle class people have a mean of 14.19 and a standard deviation of 2.38 with 675 degrees of freedom. And so if we lose 1 degree of freedom for estimating the true population standard deviation with the sample standard deviation, we're down to 674. And so that's higher than the highest value listed. We're just going to use this infinity column. And so the value that we'll use for 0.05 alpha two-tailed test is going to be 1.96. So for middle class, we're going to use a t-value of 1.96. And then for lower class, we're going to use a value of 2. So let's plug these numbers into our formulas and calculate our results. Okay, so first for the lower class people, we're going to take their sample standard deviation, 3.18, divided by the square root of their sample size, remember 89 people, and that's going to give us this estimated standard error of the mean, and that's a value of 0.337. And so we can calculate the confidence interval by taking their sample mean, 10.34, adding, subtracting the product of the t-value, 2, times the standard error. And when we do the calculations, we get a range from 9.67 to 11.01. And so we can say that we're 95% certain that lower class respondents have between 9.67 years of education and a little over 11 years of education. Now for the middle class respondents, we'll take their sample mean, 2.391, divided by the square root of their sample size, 675. We get a standard error, estimated standard error, of 0.092. We multiply that value by the t-value for the middle class response, 1.96, and subtract it to their sample mean, 14.19. And when we do the arithmetic, we get a value of 14.01 to 14.37. And so we can say that we're 95% certain that middle class respondents have between 14 and 14.37 years of education in the population on average. Now for question 8, we have to calculate the 99% confidence interval. And so again, we're going to use the same formula. We're going to take the sample mean and subtract the product of the t-value and the estimated standard error in this case. The only thing that's going to change here is the t-value. And so we're going to have to use the one for the 99% confidence interval rather than the 95% confidence interval. And so starting with the lower class, we're going to use a two-tailed confidence interval and a 0.01 alpha level instead of 0.05. And so again, we can't figure out the exact degrees of freedom. We're looking for 88, and that's between 60 and 120. So the value we're looking for is between 2.66 and 2.617. So I'm just going to choose 2.66 because I think it's the closest one. And again, for the middle class respondents, they have 674 degrees of freedom, which is going to be bigger than the biggest value listed here. And so we're just going to use this column, and that means we're going to use this value, 2.576, or 2.58 if we round it. And so to calculate the confidence interval, we're going to have the same standard error for the lower class respondents, and that's the sample standard deviation 3.18 divided by the square root of 89, the sample size. That gives us an estimated standard error of 0.337. We're going to put that value into our formula times the t-value, 2.66, plus and minus the sample mean, 10.34, and we get a range from 9.44 to 11.26. So we can say that we're 99% certain that the lower class respondents have between 9.44 and 11.24 years of education on average in the population. And for the middle class respondents, we basically do the same thing. We're going to divide their standard error by the square root of their sample size. We get the same standard error, estimated standard error of 0.092. We're going to use the t-value of 2.58 if we round a little bit. The product of the standard error and the z-score plus or minus the sample mean gives us a range between 13.95 and 14.43. And so we can say that we're 99% certain that in the population, middle class respondents have between 13.95 years of education and 14.43 years of education. And so that's the answer to that question. And then question 9 basically says, what happens as you increase the level of confidence? What happens to the size of the confidence interval, and how does that affect precision? Well, we can see that as we increase the level of confidence, the width of our confidence interval got bigger, and that means that the precision of the estimate is lower because we have a harder time pinpointing the exact value of the population mean because we have more values to choose from. So there's a trade-off between level of confidence and precision. As one goes up, the other goes down. All right, for question 10, we're given the following scenario. We're told that nationally, doctors working for health maintenance organizations, HMOs, average about 13.5 years of experience in their specialty with a standard deviation of 7.6 years. And so this is the population information. So 3.5 years of experience is population mean, and 7.6 years is the population standard deviation. And now we're told that the executive director of an HMO in a western state is interested in determining whether or not doctors have less experience than the national average. That is, only in those western states. So they take a random sample of 150 doctors, and they show that the mean is only 10.9 years of experience. And so we're supposed to test the hypothesis that doctors in this HMO, that is in the western states, have less experience than the national average. And we're supposed to use an alpha level of 0.01, and we're supposed to follow the 5 steps in hypothesis testing. So the first step is to basically state our assumptions. So we make an assumption about the method of sampling, and so we're going to assume we have a random sample. We make an assumption about the level of measurement of the variable, and so years of experience is measured on an interval ratio scale. And then we're going to make an assumption about the shape of the sampling distribution. And because we have a large sample that is more than 50 or about 30, we don't have to assume anything about the shape of the sampling distribution. We know it's normally distributed based on the central limit theorem. So no other assumptions required in this case. For step 2, we're going to write our research and null hypothesis, and we're going to state our alpha level. And so our research hypothesis, H sub 1, is that mu sub y, which represents the true population mean for the western state HMOs, is less than 13.5, which is the average for the entire nation of HMOs. And then our null hypothesis, the thing we're actually going to test here, is that the population mean for the western state HMOs is equal to the mean of all HMOs, 13.5 years. And then we're going to choose an alpha level of 0.01. Now our third step is to select a sampling distribution and to specify a test statistic. And so we have basically 2 to choose from. we can either choose the z-distribution or we can choose the t-distribution. So which one is best? Well, in this example, remember that we're given the value of the true population standard deviation, 7.6 years. And so we don't have to estimate it with the sample standard deviation. Therefore, we can use the z-distribution. And so this is the formula that we use. So it tells us that we have to take the sample mean, subtract the true population mean, and we have to divide that by the standard error of the mean. And in this case, the standard error of the mean is going to be equal to the true population standard deviation divided by the square root of n. If we didn't have the true population standard deviation, and we had to estimate it with the sample standard deviation, we would have to use the t-distribution with n-1 degrees of freedom, like we did in the earlier examples. Okay, so the next step is basically to calculate the value of our z obtained. And so we're going to plug the numbers into the formula. And so remember that our sample mean for the Western state HMOs was 10.9. So 10.9 minus what we think is the true population mean under the null hypothesis 13.5, divided by the standard error, which is 7.6, the true population standard deviation, divided by the square root of the sample size, 150. When I do all of the arithmetic, I get a value of negative 4.19. So that tells me that 10.9 is over 4 standard deviations below the mean. Now, how likely is that? Well, what we could do is we could look this value up in the table, and we can figure out the probability of getting this actual result. In other words, we can calculate something called the p-value. But first, let's take a look at our rejection region. So for step 5, we have to basically interpret our results and make a decision. So under the null hypothesis, we have the following situation. So here's the sampling distribution. We're doing a left-tailed test because, remember, our research hypothesis is that our sample mean is less than some value. And so that's going to be completely evaluated in the left tail of the distribution. So we have a left-tailed test, a one-tailed test. We have a 0.01 alpha level. And so if we find some value that's in this tail, we can reject the null hypothesis. And so let's look up 4.19 in the table. Again, positive values aren't going to be listed, so we're going to have to use, negative values aren't going to be listed, so we're going to have to use the positive value. But 4 is the largest standard deviation listed. And so this is even bigger than that largest value. And we're looking at column C, the area beyond the z-score. We don't know exactly what it's going to be for our particular z obtained, but we know that it's going to be smaller than 0.0001. So in other words, there's less than 1 in 10,000 chance that we get a sample result like this. And we said that as long as something occurs by chance about 1% of the time, we can reject the null hypothesis. Well, this is occurring less than 0.0001 times. And so this is even less frequent than what we think is sufficiently infrequent. And so because our p-value, 0.0001, is less than our alpha level, 0.01, we can reject the null hypothesis. And so let's go back to our hypotheses. That basically means that we can reject our null hypothesis that the mean for the Western state HMOs is equal to the average of all HMOs throughout the entire nation. And we have more evidence for our research hypothesis in this case, that the actual value of the average for the Western state HMOs is less than the average value for all state HMOs. And so it's going to be less than 13.5, and that's the answer to this question. Now, in terms of variations on this question, the only thing that can differ is the research hypothesis. And in this case, it was a left-tailed test. But suppose that the question said, test the hypothesis that doctors have a different level of experience than the national average. Well, in that case, you would have a two-tailed test, and this would be non-equal to. And then our rejection region in that case would be equally split into both tails of the sampling distribution instead of just one tail. Another variation is that you could be given only the sample standard deviation instead of the population standard deviation, in which case you'd have to use the t-distribution. And another variation is if you use the t-distribution, you'd have to use the t-table to compare your t obtained to a critical value. And if your t obtained is bigger than that critical value, you can reject the null hypothesis. And so that's basically the only way a question like this can vary on a final. So just be aware of all those different possibilities, and you should be able to do fine.